Today we're going to talk about something which is a very fancy looking idea, but it's not too complicated once you know what it means. It's called sigma notation. It's just a way of showing a very, very, very long sum of repeated expressions in one short version. So this is an example of sigma notation. That big Greek thing looks like an E is actually the Greek letter sigma. What this sigma notation means is we're going to add up 3n over and over and over again. That's all it means. 3n plus 3n plus 3n plus 3n. That n has a name. It's called the Index of Summation. And it changes every time we add another 3n. So we're going to add 3n when n is equal to 1, and then 3n when n is equal to 2, and 3n when n is equal to 3. And we're just going to keep going until we get to this last number here. So we need to know first where to start. That's the 1. That's the first n number we're going to plug in for n. And then where to stop. That's the number 10. And we're just going to plug in every single number in between 3 times 1. I'm sorry, I shouldn't say every single number. Every single version of 3n in between 3 times 1 and 3 times 10. So that's 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4, all the way up to 3 times 10. Now, we can do that addition in our heads if we wanted to. But for problems where the addition becomes much bigger, and we have much longer summations to do, it is helpful to use the same formulas we learned today for an arithmetic sequence or series. Now, one thing that's really, really important you have to identify before you do anything else is you have to be able to say that this sequence, the series, really is arithmetic, which we learned means that each number in the series is added by the same constant amount, that common difference that we talk about. Well, if I'm adding these numbers, it is 3 plus 6 plus 9 plus 12 all the way up to 30. So I will be adding 3 every time to get to my next term to combine. And since each term is 3 more than the last term, we would call that an arithmetic series. It is really important to identify whether or not that is true. Oh, I'm sorry, put that in the wrong spot. To identify whether or not that is true, whether or not the series is in fact arithmetic, because if it's not, we don't know how to add them up. The way you're going to know that a series is arithmetic is if the formula that's being summated, that's the formula I have in here, that 3n, if that formula is linear, then the series is arithmetic. So it's a connection between something we've learned before and something we're learning now. Arithmetic sequences are very similar to linear functions. If that formula is linear, then the slope of the linear function is the common difference of the arithmetic series. So we can right away say that d is equal to 3. We can also figure out how many terms are in the series by thinking about where it starts and where it ends. Now, you do have to be careful about this one. It's tempting to say, like, oh, we'll just subtract where it starts from where it ends and say 10 minus 1, so there are 9 terms. But do a quick count in your head. If you start at 1 and keep going through 10, that's actually 10 terms. Because we don't want to subtract the 1, because we're counting the 1. So what we're really going to do is subtract the number before the 1. So the way I like to write it is you take the last number for n that we're going to use. Notice how it's not the last number from our series. Sorry, it's not the last number from our series. It's not the 30. It's just the last number that we're plugging in for n. Subtract the first number that we used. It's that 1, that beginning. But because that's subtracting 1 too many, we'll add 1 back. So in this case, that ends up being 10. Remember the formula for S sub n is n over 2 times a sub 1 plus a sub n. Well, we just identified that there are 10 terms, so we can call this 10 over 2. If I just figure out what the first term is, well, we already said that's 3. And what the last term is, well, that's 30. And we can get these just by plugging the first term into 3n, and then the last, sorry, I shouldn't say the first term, the first n into 3n, and then plugging the last n into 3n. That'll give us our a sub 1 and our a sub n. So we can finish this off by putting the a sub 1 plus a sub n into our formula, and that's 5 times 33, or 165. The key here, because what's being added is this sigma notation. So that's what I want to focus on here. So what we need to be able to do is kind of go backwards also. So here's a series. Let's see if we can figure out how to put it into sigma notation. First off, we want to figure out what formula we're adding over and over and over again. Well, it's 3 times something plus 5, and then 3 times the next thing plus 5, and 3 times the next thing plus 5. So what we're summing up here is 3n plus 5 over and over and over again. And we can tell by looking that the first n we plug in is 2, and the last n we plug in is 31. So there's my sigma notation. Because this is linear, that means we know our series is arithmetic, and we can use the formula for S sub n of an arithmetic series and then filling in the missing pieces, we can say a sub 1 is, our first term is 3 times 2 plus 5, so that's 11. Our last term is 3 times 31 plus 5. That's 93 plus 5. And our n, the number of terms we have, be careful, it's not 31, because this time we only started counting at 2. So 31 minus 2, and then add 1 back, because we don't want to forget about the 2. So that's 30. So our S sub n is 30 over 2 times 11 plus 98, or 15 times 101, or 1515. It would help if I could, add. That's 109, not 101. So that is 1500 plus 135, or 1635, I think. The last example I want to do is turn some sigma notations into sums. So what we're going to do is take the sum of the square root of 2n from 4 to 9 and just write that out the long way. Well, that just means taking the square root of 2n plus the square root of 2n plus the square root of 2n until we're done. Well, we need to know where to start. The square root of 2 times 4, because we're going to use our first number is 4, plus the square root of 2 times 5, plus the square root of 2 times 6, plus the square root of 2 times 7, plus the square root of 2 times 8, kind of run out of space here, plus the square root of 2 times 9. And this is not going to be very pretty. That's root 8 plus root 10 plus root 12 plus root 14 plus 4, because that next one's a perfect square, plus root 18. And you know what? There's nothing I can do with this. This is not an arithmetic series. There's no formula I can use to add all of these up, because this is not linear. Sorry, it is nonlinear, which means that the series is not arithmetic, and I don't have a formula to fill it in.